Welcome to the Solaritive University Knowledge Exchange. In this series of science-based toolpaths, we're going to see part 2 of the mechanics of milling, where we'll examine the work involved in milling. Now that we've looked at force, we're going to move on to work, energy, and heat. Work is done when an object is displaced or moved by a force acting on the object. Mathematically, work is defined as the force times the distance. Energy is required to perform work. In milling, the machine tool provides the energy needed to do the work by the cutting tool. Heat is released when the end mill works in the material. And that heat wears out the tool, and this happens more quickly when heat is not carried away with the chips. In our last video, we watched how force changes as the tool rotates through the material. Now we're going to observe the work being done by the tool using the same example of a 25% step over. As you know, once the tool enters the cut, the force is at its maximum. But the work is just getting started. So at this point, no work has been done yet. Once the tool is rotated completely through the material, the cutting force has undergone its entire displacement. Therefore, all of the work on this cut has been done, and that's why the value has reached its maximum. As seen in the previous video, adjusting the feed is necessary to maintain the maximum chip thickness, and therefore maximum cutting force, when setting the step over to less than 50%. But step over settings have a greater impact on work, even when the feed has been adjusted appropriately. Notice that the blue tool on the left will start cutting as soon as it rotates, but the green tool on the right will not. Consequently, the tool on the right won't start working until the tool on the left is more than halfway through the cut. Even though the maximum cutting forces on these tools are the same, the work done is not. The tool on the right has only done 1/3 of the work done by the tool on the left. Consequently, very little heat has been put into the tool doing less work. So, after adjusting the feed per tooth for a light step over setting, it will be necessary to adjust the speed. Our graph on the right is now a function of time rather than angular position of the tool. In this example, the green tool on the right will be set to a speed 3 times faster than the blue tool on the left. In 8 milliseconds, we'll see the tool on the left rotate through 90 degrees, while the tool on the right will rotate through 270 degrees. Now that the speed is 3 times faster, the tool with the 10% step over on the right is doing just as much work as the tool with the 50% step over on the left. Notice how much farther the tool on the right traveled during the 8 milliseconds. It turns out that it was feeding 5 times faster due to the adjusted feed per tooth and the adjusted speed. It's no coincidence that the difference in feed is the inverted ratio of the step overs. As milling continues, the work these tools are doing will continue to generate heat. As we've seen, to get work out of the tool, the speed needs to be increased when the step over is light. Adjusting speed is not as simple as adjusting feed per tooth. Speed adjustment requires a starting or a reference point. The table shown here illustrates a speed factor when referencing a known, reliable speed at a 50% step over. In this presentation, we used a 10% step over where the speed was increased by a factor of 3. Thank you for watching our presentations of science-based toolpaths from Solaritive University.